Hello, everyone. Thank you for joining today for this GRSS webinar. My name is Manil Maskey, and I'm the chair of the Earth Science Informatics Technical Committee. I work for NASA, where I lead several AI initiatives for the Earth Science Data Systems program at the NASA headquarters, and I also lead a team of data scientists at NASA's Marshall Space Flight Center in developing applications of AI using Earth observation data. So today I have about 20 minutes for this presentation and about 10 minutes for discussion. Therefore, I'll first briefly talk about the ESI activities, and then at high level, talk about today's topic, which is AI, ML, and data systems. It's not moving. All right. So the objective of the ESI Technical Committee are to focus on applications of informatics on remote sensing and geoscience data, essentially trying to maximize the usage of Earth observation data using technology. To provide a venue for informatics professionals like us to exchange information and knowledge, and also be proactive in looking at the latest technologies and determine how we can leverage those technologies in geoscience domain. The area of interest covers several topics, including data policies, data stewardship, and computing environments, and ultimately supporting the open science initiatives. So there are several recent activities that ESI is conducting. These are grouped here. Some of the ongoing activities include the data science competition that we're running, trying to understand, use the community to build applications, AI applications around the training data sets that we collect. We also have another data science competition that will be running in August. And we have several other projects related to machine learning. We are also engaged quite heavily with the community, as you can see the list there. And we are engaged with our members in terms of IGOS sessions, continuous webinars, workshops, and things like that. And obviously, some of them were recent ones were canceled or postponed due to COVID-19. So this is one of the activities that we're running that we just concluded, by the way, is creating this curated training data set, large-scale training data sets for diverse flooding scenarios to scale machine learning applications. And this was one of the data sets that was being accepted for a challenge later in the summer. Where we utilized students across the US and Europe, where they worked with the domain experts to create these labeled data sets. Last year, we also did a workshop to understand the issues related to training data sets, and the more detail about that is out on a report, and there is also an AGU articles related to that. So this is the data science competition that's currently being run. This is a partnership between ESI, NASA, and several industry partnerships, participants. This is trying to understand how we can predict wind speeds by just looking at satellite imagery. And Radiant Earth was the main organizer for this event, and there's still time to participate if you're interested. Well, a bit of news, we have a new working group under ESI now. It's the High Performance and Disruptive Computing in Remote Sensing, led by Gabriel Cavallaro and Dora Blanco-Heras. The objective here is to connect a community of interdisciplinary research who are focused on high performance computing and disruptive computing for remote sensing. The main topics include not only computing platforms, but specialized hardware, looking at GPU, FGPA, and how that can be used within remote sensing community, and also looking at quantum computing, which we haven't done in any of our TC. So this provides a little new niche for a technical committee to be looking at some of these up and coming technology and utilizing existing infrastructure like high performance computing. They've already outlined several activities for coming year, and more information will that come in March when we have another webinar focused on this working group. So now to today's topic, which is the NASA Earth Science Data Systems Perspective on Artificial Intelligence and Machine Learning. So we all know NASA has a big missions, right? And its strategic goal is to observe our planet comprehensively. So these large missions obviously produce a lot of data. This shows just the missions that we have in planning at some stage of planning or under operations through the year 2013. So the data collected by all these missions are managed by the NASA's Earth Science Data Systems Program, or known as ESDS program. And it manages through that lifecycle as shown in the right here. So we've been doing that for last 25 years and with an open data policy. And due to that policy, research development and new applications in various sectors, including commercial sectors, have produced many innovative applications around those data. The problem now is that we have about 40 petabytes of data currently in the archive, but in coming few years, you saw in that missions diagram, the data is projected to reach of an archive of 250 petabytes. So why is it important to provide data stewardship for the data that we collect? To answer that question, we need to look at this statement in the NASA's Advisory Council Ad Hoc Big Data Task Force report, which states that half of all science results come from archive data. So the development and maintenance of robust archive is of a real importance for scientific community. However, there are numerous challenges that are presented by these future missions, which includes improving the efficiency of data systems operations, providing means to access and process these large petabytes of data quickly, and sometimes provide seamless data and information discovery while keeping these open data policies that we have. So obviously we're looking at emerging technologies to address these challenges, specifically cloud computing, where the data is moving now, and AI technologies. So today I'll briefly focus on artificial intelligence and machine learning aspects from the data system side. I'm sure most of you already are familiar with what the term AI and ML means, but this figure here in a nutshell summarizes what the terms mean, right? And in terms of adoption, these five components I showed in the right is key to acceleration of AI, ML within science and other areas. So with regards to rapid adoption, we also did a study to understand current landscape of AI, ML within earth science. So we did a literature survey of earth science papers over the last 11 years and found that rapid adoption of AI, ML within the earth science community, and it has significantly increased in the last several years. Across earth science, there's a 90% increase in papers published within AGU, and about four times more in SPIE papers, and about tenfold more in IEEE papers. So we also did a deeper dive, and we observed many cases in where the problems and acceleration both were related to pointed back to the data, right? So data is a key to this acceleration. So data systems cannot only adopt AI to improve its services and operations, but it can also enable and accelerate AI research for our science, because we know that data is key here, right, to the advancement. So as an adopter of AI, we're focusing on on the challenges that I've shown here, which includes improving the efficiency of data systems operations, providing means to access this data quickly, and aiding in information discovery of those using those data. So as an enabler of AI, practical steps to broaden and then accelerate the use of AI ML within earth science includes wider adoption of open science principles as shown here. And if you go into a little bit of detail, breaking these components down, close collaboration with geoscientists and ML researchers can make quick progress in a team science approach. ML research for earth science can accelerate by facilitating open AI-ready data sets and platforms to build complex architectures to solve complex problems. Benchmark data sets, which we are working quite heavily within ESI, and challenge problems have played an important role in driving progress in AI by enabling rigorous performance comparison and could play a similar role in advancing science, earth science as well. And obviously open source code, open data, open platform, and open access will better position ES community, geoscience community to take advantage of rapid development in ML. So this is a high-level AI architecture for the data systems that we envision. One that utilizes AI to power our core services and also enables AI research using our data. As I mentioned earlier, the data and services are migrated to the commercial cloud. It allows us to leverage existing AI services and also leverage those technologies close to the data, as shown here as a data lake. And that also enables us to create a pipeline where we can quickly move research and development into a production where data can be flowing in real time and machine learning applications can be applied using that pipeline. So in terms of examples, I'm going to show you very quickly a few examples of how we are incorporating AI. So this one is where we are using AI ML to maximize information and knowledge discovery capabilities. So the reason behind this concept is to take advantage of data-driven technology like AI to provide advanced search capabilities on big data that we have. What I mean by that is that the search capabilities are currently limited to predefined sets of facets, right? And so the user needs to know ahead of time what those facets are, what geophysical parameters are relevant to what they want to study, and etc. So imagine searching for 40 petabytes of data using such query and about 250 petabytes in 5 years' time. So this work provides automated event detection, which is used to catalog earth science events in an event database, allowing a novel way to explore large archives of data. So here's an example of typical data exploration, right? A studying of fire events, let's say. So users can go to visualization tools such as the NASA Worldview, very widely used tool, where the user notices the smoke in true color images. Then to further investigate the user turns on the thermal layer and notices the fire. So once you locate the fire, the next step is to use the search tool to find the science data using the search interface like this. This is the NASA Earth Data Search platform. In this case, user uses the search term fire and uses use the data and time to filter down to the data file that they need. So alternatively, what if you could let the machine learning do the identification of all these fire events in the archive data? So this video demonstrates the performance of a ML algorithm for smoke detection that was applied for the Kincaid fire on October 27, 2019, the same fire that the user wanted to study in previous slides. So the color indicates here the probability of pixels being a smoke pixel. Here, pixel level CNN was applied and the probability of pixels being a small pixel or not were being determined. So using this approach, every 15 minutes, we can run this algorithm in a continental United States as the data is being streamed. So the previous example was a bit easier because NASA Worldview visualization tool already had a thermal layer that could be used for hotspot detection of fire events. But in case of events like high latitude dust, as shown here, which also plays an important role in atmosphere, can we automatically capture the occurrence of this high latitude dust events in the regions that are very susceptible to this phenomena? So here you can see another example of a deep learning technique applied on archive data to identify these phenomena. Here is another type of event, transverse cirrus bands, which are useful in air turbulence, which are known to create air turbulence, and is important atmospheric phenomena for air travel. So here, another technique was applied. Deep learning technique was applied to actually locate this within and create this bounding box around these events, so they can study and create a long time series of these events and study what patterns emerge within the archive data. So once the model is evaluated and optimized, the model is deployed in a production environment, and I'll talk about deployment a little bit later. What this allows is a search interface or detection interface for all these phenomena in one place, and people can just come here and look at all the events using one single tool, and look at and figure out one that interests them and start studying that event in detail. Right? You can also do a climatological study if they want, since the data goes back so far, and you can apply these algorithms across the entire archive. It allows them to study these in detail. See, the other area of focus is in adopting AI is the augmentation of data stewardship processes. So what I mean by that is we have a lot of manual steps which are very subjective that we do in the data stewardship processes. That creates inconsistencies, and if we can automate some of that using AI techniques, that will provide consistency in downstream applications like search and discovery, right? So this particular application is for that, where we're trying to create these science keywords which are important in data discovery. And can we automate that process by looking at scientists provided abstracts for these data sets, so that the curator doesn't have to subjectively determine these scientific keywords. So to approach that, we approach using natural language based processing based approaches, where we looked at corpus of scientific journals for knowledge discovery and applied these work to vec type of neural network, which are very domain specific because we are using the source journals, our science journal as our source, right? So that creates a knowledge base that can be used to create this neural network that uses these abstracts, science provided abstracts, and maps that into science keywords. I'm not going to go into detail due to time, but this is the architecture that we're using, basically using the abstract as the input and coming up with the science keywords. So the other aspect is a need to transition developed models into a production type of environment, right? We can write a paper. Usually this is what the machine learning in literature looks like. And for most of them, they publish a paper and that's where the research ends, right? But there are for application purposes, we need to go a little bit further and create this deploy this in a real data and put some sort of interface so that people can understand what those numbers that are coming out of these models actually mean. But it's a difficult task. Before we do that, we need to ask you questions, right? As outlined here. How do we ensure the confidence of the model over time? meaning that the incoming data will change as we apply the model over time, which means that we need new training data and subsequently new models. And there are additional requirements like this I have shown here that is critical to successful deployment to production. So without going into detail, this is an example of wind speed detection model running in production, where in case of a hurricane outlook, storm outlook, it automatically goes and grabs the track of the hurricane, predicted track, and start collecting images, making predictions, comparing with the observations, and ultimately learn from that predictions and retrain the model. And so this is how we are using a production pipeline in cloud to create this production application. Another example is this COVID-19 dashboard, where AI models to detect shipping and airport activities to understand the economic impacts of COVID-19. And here, obviously, to detect those features, we need high resolution imageries, which we do have access to. And we productionize these using cloud data processing, cloud platforms, and automated pipeline that we are developing that we're generalizing for all these AI applications. So I went through those very fast due to the time considerations here, but here are some resources that you can go into, look at some of those applications that I demonstrated. And if you have questions, you can always contact me. If you haven't already joined the technical committee, please do so using the link there. We will have another webinar in March, I believe, talking about the new working group. And thank you for listening today. And if you have any questions, please don't hesitate to ask. Thank you.